Hello everyone, my name is Yu Hong Kong, and I'm here to present my EE538 final project. So let me start by introducing the motivation and background of this project. In the course, we were challenged to build a mapping application that leveraged data structures and graph algorithm to solve real-world spatial problems. The goal was not only to deepen our understanding of algorithmic concepts, but also gain hands-on experience in developing a comprehensive software project. So in this project, I finished the following main features, which is spatial search retrieval, path planning and optimizations, graph structure analysis, and spatial relationship operations. I will mention of the functions later on. For spatial search retrieval, the autocomplete function the application supports the autocomplete functionality, allowing the users to quickly find locations by typing partial names. For example, if you enter a CH, the system will suggest location just like Chick-fil-A or Chevron, Chipotle, whatever the location that has the prefix of the input. And users can also search for specific locations, and if the input does not match exactly, the system will suggest the closest alternatives. For example, if you have made a typo in Libby library and the system will ask you, did you mean the correct Libby library? In addition, user can browse all of the available location categories and retrieve all locations within a chosen category, such as cafes or libraries or bakery. Yeah. And a major part of the project was implementing path planning algorithm. The application can calculate the shortest path between two locations using classic graph algorithms such as Dijkstra or Bellman-Ford. So you just basically type in the start location and destinations, and the system will calculate the route for you and the distance by using Dijkstra and Bellman-Ford algorithms. And this is the predict path compared to the route provided by Google Maps. So they are actually the same. For a more complex routing, which is the traveling salesman problems, I implement the brute force backtracking and two-opt optimization methods. The input n is the number of the locations in the traveling salesman problems, and the system will just randomly select n locations and use the three approaches to find the path. So this is the brute force method. This is the backtracking methods. This is the two-opt approach. And I compared their performance across the different number of locations. It was all tested on my MacBook Air M3 with 16 GB RAM. And each of the pros was tested 10 times, and I compute the average run time. As you can see, two-opt approach has the least run time, so it's the most efficient way. And the system also supports planning a route to visit a custom list of location, optimizing the total distance travel. For example, if you want to go to Rolf's, Libby Library, Starbucks, Just Right LA, and Trader Joe's, those five locations, the system will compute the best route for you to have the minimum distance to visit all of the locations. And in this project, it also includes some advanced graph analysis features, such as cycle detections and the topological sorting. For cycle detection, users can just input the grid boundary in latitude and longitude. The system will detect whether in this area there exists a cycle or not. Another function is the topological sorting. For example, they're given a set of locations and some dependencies, and the applications can output a valid visiting order. For example, you want to go to Rolf's Levy library and just write LA, and the dependencies are you have to go to Rolf's before Levy library. You have to go to Rolf's before just write LA. You have to go to Levy library before just write LA. And the system will provide the correct order, which is visiting Ralph's first, and then Levy library, and then it's just right LA. Another function that checks whether it is possible to travel from a source to a destination under certain constraints, such as the limited fuel capacity. For example, if you starting from Rawls, you're heading to Levy library, and you have only 0.05 volume of gas in your fuel tank, then yeah, you can make it. But if you only have 0.01 gallon in your gas tank, then you could have made it. The find nearby function allows users to search for a location of a certain type, like cafes, within a special radius and a chosen point. This is useful for discovering amenities near a given location. For example, you wanted to explore cafes around Levy Library in radius of 10 miles. The system will just show off the possible locations on the map and list it out. So during this project, I encountered several of the technical challenges, right, such as optimizing the TSP problems, especially for large data sets, required careful consideration of time complexity and memory usage. I also ensured that the application could handle invalid user input gracefully, providing suggestions and clear error messages. Version control played a crucial role in managing the codebase. By using Git and GitHub, I was able to track changes, experiment with different approaches, and collaborate with effectively when needed. Yeah. And this project provided a thorough experience of the entire software development lifecycle, from initial design and the algorithm selection to implementation, testing, and optimization. I was able to apply the skills I learned from the lecture directly into real-world scenarios. This deepened my understanding of both C++ programming and algorithmic problem solving. And thank you for your attention. I'll see you next time.